Welcome to those of you who have joined us early. We will begin in a few minutes. We have about 2 minutes before we get to our start time. So thank you for joining. Good afternoon and good morning, colleagues. I am Sherry-Ann Farquharson, Knowledge Management and Capacity Development Expert for the Caribbean Center for Renewable Energy and Energy Efficiency. It is my pleasure to welcome you to the 5th Regional Universities Networking webinar. For those of you who don't know, the Regional Universities Network, or the RUN, is a network of excellence for research and education on sustainable energy. The network is multi-institutional, covers universities, private and public sector across the Caribbean. The network allows participants to jointly define and share curricula, programs, collaboratively develop agenda and projects for basic and applied research, and develop policies and good practices for the sector. In today's webinar, we will explore integrating inverter-based renewable energy generation into low inertia power systems with Mr. Clint Alley. Clint holds a master's degree in power systems from the University of the West Indies, St. Augustine, and is currently pursuing a doctoral degree with the Electrical Energy Systems Group at the Eindhoven University of Technology. He is a lecturer in the Department of Electrical Engineering at the Antondecom University in Suriname. So a few housekeeping matters before we hear from our main presenter. Your mics are muted. However, if you want to participate in the discussion, you may raise your hand if you wish to ask your question live. or you may type your questions in the Q&A throughout the presentation, and we will have that discussion at the end. I invite you to listen, to get ready to ask your questions and participate in the discussion. And at this time, I hand over to Clint.
Okay, good day everyone, and it's great to have you here at this secret webinar. I'll just start to share my screen and then we can get on with it. Also, thank you, Sherry-Ann, for the introduction. I hope my screen, my shared screen can be seen.
Yes, you may go ahead and we're seeing it clearly.
Okay, great. So this topic is of high research value at the moment regarding inverter-based renewable generation into specifically low inertia power systems. It is current research that I'm involved with at the moment in relating Anton Kom University in Suriname and Eindhoven University in the Netherlands. So let me see if I could go to the next slide. So I could like to mention some research that currently we are doing at the Anton Kom University in Suriname before I get into the main topic. Those include research assessments of PV and wind sources. We are also looking at energy performance of PV systems. Energy performance, not really relating to power quality, more on the energy side. And another topic that we are highly involved with is the integration of inverter-based renewable generation, and in this case, mainly PV. That's a topic of today, and there is a collaboration with UB St. Augustine and also with the University of Eindhoven in the Netherlands regarding to this kind of studies. So, so what's traditional power systems? For years and years they have been there, and little problems with them. You know, the input source is controllable. You have a diesel generation or a hydro power system, and you need to regulate frequencies. So you need some power in the system, and you open or close some valves, and you can easily do that. Furthermore, traditional power systems, they were all the years mainly good in regulating frequency and voltage, because it's due to the synchronous generation in the grid, they have a strong coupling with the electromechanical coupling with the grid. This is very useful for having the grid reacting to events in the grid, this electromechanical coupling. Then one other great attribute that we had with the traditional power system is that we already have, everybody is speaking about storage, but we already had storage in the power system in the form of kinetic energy, which are in the rotational form of rotational generation. So when you have large synchronous generators, you have some form of inertia storage in kinetic energy, and that's also very useful for regulating frequency. Now, so then comes the renewable generation units, and as you all know, these are integrated to the grid via inverters. So the problem mainly starts with, let's say, first of all, that the input source is very difficult to control. PV and wind is an example, is a very fluctuating source, so that makes it, I don't have a valve that I can open or close, or at any time I would like the sun to shine or the wind is not readily available. So that's one problem. Then the problem that then occurs again is the one that I was speaking about today. That is a decoupling of these sources with the grid, because as you know, all of these sources they connect to the grid through power electronic converters, and this will render this disconnecting of these sources to the grid via power electronics will render the dynamics on the grid. So what we had before as a tradition, the dynamics we had before will now be different in when we put renewable generation via power electronics converters, connect them to the system. And it may even be so pushed to the limit that the variables of the grid in terms of hertz, the frequency and volts, they may be moving around to unacceptable limits. And of course, you don't want that situation, because then the grid will be an unstable grid and with other consequences. Furthermore, different type of controls will be necessary for these kinds of inverter-based generation, not the general controls that we are used to for synchronous generators. Now, these generators will require different kind of more complex control, type of controls. So let's see if let's zoom in on one of the variables of the grid and one of the consequences of integrating inverter-based renewable energy. Is less if you can look at the response of the frequency into an event, a short circuit or a loss of a generation or something. Then you can see that in this graph, there are basically 3 periods for recovering the frequency, whether it was 60 or 50 hertz, back to the pre-event value. So the first response that usually occurs is the inertial response. That's release of kinetic energy from the rotational generator to the grid. And this time rate of change of frequency, termed Rokoff, is very important. It's a first stage of bringing the frequency back to the pre-fault condition. And it's very important for also preventing the frequency from declining fast, preventing it from reaching a very violating under limit values. And in general, helping out the second response that comes from the grid, that is basically the primary response. And that's where the governors kick in from the generators, and the governors can react to the frequency by injecting real power and trying to bring the frequency back. And obviously you will have a third period, which is a secondary control, where the frequency can be restored back to the pre-fault condition. So the main issue here is this Rokoff, which is traditionally directly tied, electromagnetically coupled to the stored kinetic energy in the shafts of the generators. And this helps this route to prevent this steep decline, to be slow it down a bit. So now what happens? By the way, this Rokoff, this dynamic here is governed by this equation, which is popularly known as the swing equation. So let's see what we have in the in island grids, for instance. In island grids, what you have small generators, small diesel generators, and Suriname we have hydro generation as well. But yet these inertia of these generators, they are in, if you look at the inertia that you can have from generation units, they can range from 2 seconds to 7, 8 seconds. And in a typical island grid, you will have low inertia from these generators. So this low inertia is already kind of having the frequency jump up and down. And you can imagine what will happen if we now try to remove it and put the inertia-less systems. So if you compare these inertia constants to those, for instance, in the European, which is an interconnected grid, and therefore can build up kinetic energy in the grid, you can see that, for instance, a Rokoff in small grids will be 2 to 4 hertz per second. If you compare it to the European or an interconnected grid, it will be way less due to the kinetic energy buffer that you have, the huge kinetic energy buffer that you have. And it will be around millihertz per second to at most 1 hertz per second. So you have already low inertia grid, and now you compound that problem with adding inertia less power. So such as PV, which obviously the input is varying, and this is a decoupling I'm speaking about. So you have the power electronics devices connecting the PV to the grid, and that means, okay, this case is a static PV, no rotational power, but this is a decoupling here to the grid. So whether you have PV or you have wind is also being connected to the grid through some power electronic source. And even though wind may have some kinetic energy, it is not directly electromechanically coupled to the grid because of the power electronics converter. So whatever you put behind the power, in front of the power electronics converter, whether it's somebody driving a bicycle, cycling, and a dynamo, or I don't know, something, it will always be some power electronics, and it will be decoupling. And that is decoupling the inertia that would have been available with the grid. So we are compounding the problem now. We already have low inertia, and now we are compounding the problem by adding inertia less, or decoupling of the sources. So let's look at what this may result in. So this is a measurement on the Bonaire Island, the island of Bonaire, and you can see that this is the frequency here. There occurs in this moment a event, and the frequency drops within 400 milliseconds from 50 hertz to around 46 hertz. And that is equivalent to around 10 hertz per second. So that's huge. If I just told you that it's usually 2 to maybe not even more than 2, and some maximally 4, 10 is really large. And that will result in problems for synchronous generators, which will have pole slipping, or you may even have other inverters connected that will come offline, because this is a very high frequency change to follow. And this is an unwanted situation in any grid. And bringing such a frequency back to nominal case would be very difficult. So this is the problem. You have low inertia, decoupling, and then the result is this this situation. So what can you do about it? So basically, what we try to do is then this slope which is going to be very steep because of the inertia-less integration. We try to bring it back to make it less steep, and you can do that with storage. You can do that with chemical batteries and or other types of storage, and you can try to compensate the ROCOF, bring back the ROCOF to what it was pre-integration of these kind of sources. So that's the whole idea, to get the ROCOF back to pre or acceptable levels. And let's see how, for instance, what is needed for this type of compensation. So obviously you need some type of storage, and you need a power electronics, of course, and you need some control technique. So two very popular control techniques at the moment is what's called virtual inertia. That's where we emulate electronically the inertia that would have been naturally characteristic of a synchronous generator. You emulate it, and you end up having that energy stored in the rotor. You have it stored in the battery or whatsoever, and you can have that kind of control technique, virtual inertia, or a fast frequency response. Both of them can be used. So let's see what's a virtual inertia. This is, sorry for this very detailed schematic diagram, but this is a schematic diagram of an inverter. And so what we have here is a battery. This would be a DC to DC converter, and this would be the inverter. And this would be the grid it's connected to. So how will this virtual inertia, this emulated inertia, be implemented? The inverter will be measuring looking at the voltage at its point of common coupling. Based on the voltage will have an angle. This is the angle. This block will be calculating this angle, looking at this angle tightly. And the derivative of this angle, the voltage angle, is actually the indication of the frequency, the rate of change of frequency. So this signal will be sent to the virtual inertia control block, which will be determined, can be based on the swing equation, is a possibility, to extract power from the battery storage and inject it into the grid in response of a change of this, in response to a change of the frequency, which again, I said, can be observed by observing this angle. So that's a basic idea. So let's see what inverters should now be required to do. So in inverters, besides the already functions that they have, such as voltage and current control and grid synchronization and optimizing power extraction from the PV or from the wind, and also fault right through. Now because of this situation, you have to require from inverter systems that they also provide more support to the grid. This in an inertia emulation or fast frequency response. The two are not the same because, as I mentioned, the inertia emulation is coupled, is emulating the behavior of the synchronous generator. So this is kind of grid supporting functions that will be needed from. This is depends also on every case. So every grid will be different and depends on how much inertia, less power you're integrating. That will determine if you really need inertia emulation or fast frequency response. These will be common functions that now have to be adopted by inverter systems. So how to study this? I will go into now how to study this kind of dynamics in the lab. So here you can see a lab setup where we have a current-fed inverter, voltage source inverter here. And this voltage source here is kind of emulating a battery. So the typical battery dynamics can be emulated by this voltage source. And here you can implement some kind of control, such as the virtual inertia in response to a frequency event. So you will then, in response to that frequency event, absorb the power, inject the power from this source or absorb it. And in a closed loop, you can have the grid emulated in kind of a hardware. Yeah, that's a correct term, the hardware in the loop simulation, studying the dynamics of the grid as virtual inertia has been implemented. So I can show you the next slide here, a typical measurement in the lab, and what would how this kind of response would look like in practice. So you can see this curve above here is the current injection to the grid, and this curve at the bottom here is the reference signal for the inverter, which is responding to an event, a frequency event. This is a frequency in radians per second. And at this moment, there is a frequency event generated in the lab. So as I just showed you in the schematic, the angle will be calculated, the grid voltage angle. And the differential of that will be this signal here sent to the inverter. In this case, the event was about 5 hertz per second maximum. And that will generate, will trigger the inverter to inject the current. As you can see at this moment, the current is being injected into the grid until that row cuff is 0. As you can see it here, now the row cuff is 0. And the inverter is stopped injecting current at this moment. So this is a compensation, the virtual inertia compensation in real life, in practice. And you can emulate this in the lab to study how this will impact the dynamic of the power system you're looking at. Okay, so there were some case studies based on this virtual inertia implementation for Suriname, and where we looked at one of the island grids that is in one of the districts of Nikeri, and ENIC. It is about a 12 megawatt island grid. And so you can see the curves here, the frequency and time curve, and you can see this black curve, that is the frequency without any PV. Now you integrate PV and without virtual inertia response, and you see that is the red line here. And you can see the steeper decline, the steeper decline of the frequency, the lower limit of the frequency. This is higher, this is lower than if you would have implemented virtual inertia response. That is the green lines. So you see the green lines result in a less steep frequency in the system, and the frequency can, in this case, be easily regulated back to the pre-fault value. So in this graph, you can see that this was a row cuff limit for this study, which was about 1.45 hertz per second. And you can see without any virtual inertia, this row cuff limit is always violated if you integrate PV and you remove displaced rotational generation. If you implement virtual inertia response, then you can correct the row cuff and have it not exceed the limitation. Of course, you can see this point is exceeding. That means that this calculation for this VIR was not adequate for such amount of PV, and this would need to be recalculated again. So this resulted in, if we don't have any without virtual inertia, that the frequency would, the Rocoff would be, the rate of change of frequency would have been around 1.83 hertz per second, but with the virtual inertia, we could bring it to 1.33 hertz per second. So that's a positive result. This was another study for our larger grids. As you know, Suriname has a set of island grids. And this one is the EPAR grid, which is extending beyond the capital of Paramaribo to other districts. And it's basically a 200 plus megawatt grid, which is also including hydro. As you know, Suriname has a large amount of hydro power. And hydro units have relatively high inertia naturally. So what we did here is looked at if we integrate PV, and we determined a limit, which was 1 hertz per second, which was the pre-PV limit, how that in Rocoff would change. And you can see that, and this is the inertia constant, this is the PV integration, and at about 30% of PV, the inertia constant in the grid has dropped to 20 because we have replaced rotational generation with PV. And at that point, the Rocoff would have been violated. So this is a nice curve to determine at what point, the Rocoff would be violated if we integrate PV. You can see that this line is without any virtual inertia. And the green line here is if you would have implemented virtual inertia, then this Rocoff here, which is the Rocoff without any PV, that you can maintain that Rocoff even though you're adding PV to the system. The limitation is here above, and you can see with the virtual inertia that this curve is more or less flat. So let me see. So I'll have to come to the final remarks because my time is running out. So let's say the final remarks are this: low inertia grids. So we have a lot of these in the Caribbean. And they are intrinsically, they will have this frequency already moving up and down. So they will, now when you replace, when you integrate a lot of renewable energy, it will compound this situation, and you will need now, there will be need based on a specific cases of course, to include inverters with functions that can implement virtual inertia or fast frequency response to maintain a good frequency regulation. Of course, as I said, every grid is different, and they would require some studies, some research to determine how much compensation is necessary, how hard the virtual inertia should be, those kind of things. There are more issues when implementing, and these regard the dynamics, the transient of the power systems. And remember, island grids, as I said, they are fluctuating more than an interconnected grid. So, and then one more characteristic of such a low inertia grid that needs attention is the low short circuit ratio, where the inverter is connected, because those kind of situations is also can create, depends on what kind of control the inverter is using, can create instability problems. So these also need to be taken into account. So I would like to, before I conclude, finish the presentation, just add some publications here that if you need to read up further underneath this of the material I have presented today, so you can take a read at these, look at these publications. So with that, I would like to thank you, and I think hand it over to Sherry Ann.
All right, thank you very much, Clint. That was quite an interesting presentation. And so now it is time for us to have that discussion. We've gotten one question so far, but I'm going to remind you, if you want to ask a question, you can write your question in the Q&A, or if you would like to ask a question live, you can raise your hand and we will allow you to unmute and ask your question. I see a number of utility colleagues and academics in the room. So I am hoping to hear from you as well as from my SICRE colleagues on this interesting approach. All right, so I'm going to start with the first question, and then we will continue thereafter. So our first question comes from Joy Ingrid dos Santos Themen. I hope I've gotten that right. She compliments on the extremely relevant webinar. So her question, not as technical, but she's a fan of solar energy and agriculture, specifically horticulture, small animal husbandry. So she's interested in the coexistence of systems, for instance, increasing the vertical installation height in case of a solar panel inclinations. So she'd welcome those in Suriname, and she's keen to hear your thoughts on that kind of a setup.
Yes, so in regards to the inclination height, of course, that is in relation to where the solar system is being installed. You know, Suriname is very close to the equator. So we have typically for maximum power extraction from the sun around a 5 degrees angle, inclination angle. But in practice, what a lot of installers actually do is they tilt the angle maybe up to 10, just to allow for what they say, rainfall or accumulation of dirt on the panel. So in terms of inclination angle for us, and against this is dependent on which part of the world you are. For us, it's about between 5 and 10 degrees. I hope that's the question as I understood it.
Okay, sounds about like it to me as well. Could you stop sharing? So since we're just doing the discussion, so we can get a better. All right, we can see you a little better. All right, great. So our second question coming in from Lilawati Manu Raming. Great presentation again. Yes, indeed, I do agree. So she's assuming that these additional inverter functions are to be installed for utility scale PV systems. So the question, what about residential scale grid-tied systems? Do these need inverter functions? And she's assuming that is there an increase in cost? What would that kind of increase in cost look like?
Yes, so in terms of having each residential unit respond to a frequency event, that's a kind of a difficult situation to put the inverters into, because they will have to be communicating with each other to not fight to regulate the frequency. So, and as of today, communication delays are an issue. And so what these kind of residential inverters will more likely be required to be doing is more not really looking at the frequency, but looking at the terminals they are connecting to, in terms of curtailing that PV power, in terms of regulating the voltage that it doesn't get too high. So in terms of regulating the frequency, and at the moment, it's more a centralized function.
Okay, all right, thanks for that. Another less technical before we dive back into the deep end. So here and there, one still hears an old taboo that solar PV is not feasible because it is too cloudy, and I'm guessing that's in Suriname throughout the year. Could you elaborate on the feasibility of solar PV for, well, not just Suriname, but for the region?
Yes, so yes, it is cloudy, and the cloudiness brings mainly the problem of the fluctuation, and less the problem of generating kilowatt hours. So in that sense, we have let's put it in this context. A typical 3 kilowatts PV residential will generate in Suriname anything between 15 to 18 kilowatt hour per day on a sunny day. So that's reasonably okay if you compare to other systems in Europe. So I would say the cloudiness is, in terms of aluminium fluctuation, maybe a big deal, but in terms of energy generation, on the average, it is okay.
Okay, all right. Thanks for that. The next question, coming from one of our SICRE colleagues. Was there any mention of how the well, he was a little late, so I'm just gonna ask you to just review in terms of the virtual inverters inertials address, do they address over frequency? Because he noticed that the plots presented look a bit like they were displaying under frequency. So how is that addressed? Is it
I'm sorry,
addressing over
you broke up.
frequency?
Okay, okay, it is clear. You broke up at the end, but I could get the question. Yes. So of course you can address over frequency. Inertia goes both ways, and while you can inject the power, you can absorb as well through the power electronics. Of course, you will have to have the battery operating and in a state that you can also absorb power. So yes, over frequency is also possible.
Okay, all right. Not sure if Agan is gonna have a follow-up on that. Um, we have a follow-up from Joy. I think the first question that we had asked was from her, and she's saying that her question also related to the experiments that are already happening related to the coexistence of solar PV systems on small agricultural projects, where they have the agricultural projects underneath the solar installation, so that the loss of potential agricultural land is compensated for. So she's saying it seems they then increase the height of the installation so that small animals can graze underneath and some horticultural activities could take place as well. So that is the kind of coexisting system that she wanted to find out more about.
Okay, so in terms of increasing the height of the solar panel, if you would have more energy production because of increasing the height or a better performance. Look, because solar, besides the irradiance hitting the panels from on top, there are diffuse irradiance hitting it from the sides as well. And giving it a tilt in a less shady area in those kind of situation may increase the performance, yes. But I would motivate you to look at the new technique of solar panels, which is called bifacial solar panels, which can also transform the solar radiation from besides the top, the bottom, collect it and have a better output and better yield.
Right. And I know that we see it a lot with wind farms where they have the agriculture taking place around the wind farms. And so it is also good to be able to use the land dual purpose.
Yeah.
It definitely is an value added in the industry. All right, so another couple of questions coming up. So thanks again for the presentation. So with respect to the systems where there is not as much injection of renewable energy, so when you have smaller percentage of renewables on the grid, what are your thoughts on anti-islanding issues occurring within the Caribbean? And for some context, for example, in the Caribbean, you may have a renewable energy share of, say, just 5%. So what are your thoughts on anti-islanding issues in the region?
Yes. Okay. So those anti-islanding issues, again, every case is specific, and let's say every grid has its own kind of sensitivity, and will fluctuate less. Some grids, for instance, in Suriname itself, some grids in the main city will have less fluctuation compared to some grids in the districts. It's of course has directly related to smaller units being connected. So if in those kind of cases, if you have an inverter that is programmed to be reacting to a very sensitive case, maybe some kind of a write-through you can consider for those kind of inverters, because you are already stuck with such a grid, and you need to have the inverter maybe accept these dynamics of the grid if they are within limits, and kind of like set the limit values on the inverter so that they can operate in such circumstances.
Okay, all right. And the second question from this participant, a problem we face in the Caribbean, primarily from those pioneers of the sector with inverters with passive methods of detecting anti-islanding, which is not the best. So how do we deal with this, those passive methods of detecting anti-islanding?
Yes, again, the inverter nowadays, obviously, a lot of inverters are made for have a market-specific usage, and they will be implemented in such a way that these kind of functions will be more applicable to some grids and to other grids not. So I think this comes down to a kind of a manufacturing issue, that whenever you have projects to implement in the grid, that you understand the grid characteristics, and that this kind of issue be discussed with the manufacturer to figure out if what kind of functions should be implemented for your grid. So I think that I can answer it in that way.
Okay. All right. One of the questions that I have is how did because I saw your lab setup. How did things change once you started doing your pilots? And how were you able to make those adjustments to see how it would actually work in the field?
Yes, so a lot of issues you can have when you implement these things, but as I said, one of the main issues is communication among inverters due to delay. And if one inverter is have to wait in terms of inverter time relatively long for receiving a control signal, then an inverter will respond to something that has already happened. So delay is an issue, and when you have these kind of systems in real time in the lab, you try to see how to go around the delay. Other developments include if you have such a hardware in the loop system, that when you're simulating the grid, that you want the synchronism among the apparatus is also very important, because if you're calculating something in the computer, and it's in real time, and it's, for instance, the time steps are larger than the response time of generator, and those whole synchronism between the things can be of a problem. Furthermore, battery emulation is also a main research topic. How to emulate batteries without having actual batteries in the lab to study how to emulate the batteries with power electronics, and put those kind of things together. Then there's the issue of what type of inverters to use, and the one I showed you that was in the lab is kind of what the term is current fed, because it's powered by solar. But that can also, and then you have different types of inverters which are more for batteries. So those kind of issue when studying these kind of systems can come into play, but they are not, let's say, problems that are that cannot be resolved in a good manner.
Okay. Okay. Um, and are you recommending this methodology to be deployed across energy systems in the region, or how much more work is there to be done before you could say this is something that we would definitely recommend that we take advantage of?
Yes, we have in the Caribbean a lot of these island grids. I showed you a case of Bonaire. So that's a very large fluctuation in the frequency, and a lot of these island grids we have all over, even in Suriname. And so yes, and if you look at South Australia, where we have two different grids, one is low inertia, one is high inertia, and they've already implemented this system to allow those two grids to be connected to each other. So these kind of functions are commercially available, and yes, based on your situation, based on the grid that you have, that you know the dynamics of the grid, you should consider using these kind of functions which are already commercially available. And through the study, try to see which kind of response type would aid with regulating frequency. So the short answer to your question is yes, definitely.
Okay. I'm really, well, you did say it's already commercially available. So I guess the timeline is that as soon as that transition could happen, or is there more that needs to be done specific to the region in terms of how it would operate?
Specific to the region, as I said, you will have to look at each grid and the dynamics, and determine for each grid if it is necessary, because this will determine, this will be a use case, and depends on how much PV you will be integrating. So if it's just a small scale, unnecessary. If you're not taking generation out, rotational generation out, unnecessary. So it's a kind of a case specific, and where it becomes, besides technically needed, also economically viable, then yes, you should implement these kind of functions.
Okay. Follow-up question. As it relates to implementing energy access programs across the region for those areas that are underserved by the current existing grid systems, one of the recommendations is to implement microgrids. Microgrids that could be islanded or could be integrated with the main grid, so they would be able to operate in both cases. Would this also help to support the integration of those microgrids, or is it just for when you have just the supply side? How does that integration would work as it relates to microgrids?
Yes, sure. The example I gave in Southern Australia, you can view that small grid as a microgrid, but it could not be connected to the larger grid because the inertia level was low, and result in more fluctuation. So this virtual inertia was implemented in that grid, allowed it to become stronger in terms of fluctuation, and thereby allowed it to be connected to the larger grids. So in terms of integrating microgrids to larger grids, these type of functions are, yes, surely necessary. I would like to point out, though, that island grids on their own, obviously, I mean, microgrids on their own, before going to the, and this is a issue I see a lot, before diving into the engineering part of the microgrid, there should be a step before where you look at the more into theory and into depth about this grid and how to control this grid and what type of controls to implement in this grid. And there are useful software out there that you can do these kind of studies before you move into the engineering. And I can mention a few. Those are PSCAD you can use, MATLAB Simulink is a good software to use to understand how this microgrid would behave before the step of engineering and implementation.
Okay, definitely interesting. And I guess one of the things that it will come down to at the end of the day is cost, in terms of how much more it's going to add. Well, cost versus reliability of the grid. How does that compare in terms of using the virtual inertial? How does that compare as a solution in terms of the reliability that it offers with the frequency correction versus how much more it would cost?
Yes. So again, this would be another case specific. Let me give an example for our Suriname situation. We have now moved on to implementing microgrids, and in this case, it is financially feasible. The reason why is because we have to move a lot of oil to power diesel generation in the interior, and besides the oil itself is a costly, that is as an unwanted situation. So these kind of situations warrant the use of these functions for the specific case of the microgrid. Obviously, this is not the case in every grid, but if you look at Bonaire, if you have these units, wind and PV, and you have invested and you want them to be online because you want to get the energy from these systems, it is useful to have them online most of the time. So in a case when you don't have such a function and it will be tripping out and out every time again, that is a situation that in terms of the payback of the economic feasibility, that those kind of situations is worth it. Yes.
Okay, all right. I'm not seeing any other questions in the chat. I will just pause. As I said, I still have a few of my industry colleagues that I have not heard from as yet. So, okay, it seems that what you have presented has been very clear. So kudos to the lecturer in terms of delivering the research. It is definitely interesting work. And it would be good to see this being deployed where it's relevant across the region. So definitely interesting work. So I will ask you if you have any final comments, recommendations, anything you want to propose before we wrap up?
Yes, let me say that I'm also available offline. My email address, I think, can be shared, and any other follow-up or questions is welcome. And I would say that if other in the region are also involved in similar research, that I welcome that we be engaged in these kind of topics. I think it's a very important topic. Besides looking at the steady state of this grid, that we need to more look at the transient dynamics of these grids, especially in our case in the Caribbean, where as I mentioned, we have small grids, they are not connected, etc. And so I welcome any research and questions regarding this issue.
Okay, all right. So we see we have one question coming in from the audience. We have a raised hand. So I'll just ask our host to allow Crispin to ask his question. Kristen, you have the opportunity to unmute. All right, not sure what the technical challenge is that we're having there. Okay, not yet allowed to unmute. Okay, there you go. I see you have the option to unmute now. Okay, all right, go ahead.
All right, thanks. Just a quick question. Thanks again for this seminar. It's been very useful, you know. And as a quick question, so basically with the inverter, we were discussing earlier is looking for disturbances, and in order to correct the disturbances, it would inject basically the current, as it was said in the discussion, right? So just for example, say we have, follow me, we have a community whereby, let's say we have 100 or let's say 50 persons generating renewable energy from an inverter base, right? Everyone is interconnected, and the power goes out, right? The power goes out from the power station, because that would be from fossil, right? So power goes out, and in this community with the 100 PV generators, they all will have been injecting. So where this the fossil would have came offline, these inverters would have been pushing electricity onto the grid, but they would not have, once it's at that level, in terms of, it may not be as far from what the fossil would have at probably 50 hertz, for example, in the Caribbean is 50 hertz. What kind of mechanism then, if we are trying to make the inverters basically remove or be able to counteract this disturbance, we need them to cut off, because with this power outage, then let's say for instance, those utility workers have to go on those lines. So those inverters keep pushing off energy onto the lines. What would be the, I mean, we know that's not what we want to happen, but in terms of trying to make inverters that basically counteract this disturbance, and then being in compliance with IEEE 47, where these inverters are supposed to come offline in 0.03 seconds. Where, I mean, I have a bit of a disjoint between trying to make them not feel the disturbance, so to speak, versus them having to cut off in order for those utility workers to probably use the line. Thank you.
Yes, thank you for the question. A very interesting question, and indeed, inverters are required to go offline in sub-seconds to allow they prevent this kind of dangerous situation. So, with regards to these kind of functions in the inverter, let's say responding to this frequency event, where, as you mentioned, that it would disconnect from the larger grid. So the inverter will, and if you have this kind of function, remember that if it is that it is required for the grid, when let's say it's a microgrid, to be moving away from the larger grid in a stable way, then this will be a transient, and this will be in sub-seconds that the inverter will be responding to this frequency event. And once the frequency is back to normal, it will be, this power injection will be gone. There is no power injection anymore. So in terms of a conflict between anti-island and this transient response of the inverter, yes, you will have to coordinate that together with the IEEE to coordinate, let's say, the priority is to keep the grid from a blackout and back to steady state. And then afterwards, you have to go fix the problem. So you will require the inverter, the kind of coordination that will have to be implemented in the inverter.
Okay.
So that, yes.
Okay, thank you.
Yes.
All right. I'm seeing a follow-up from my colleague Algon. Algon, could you just unmute and share that comment, please?
Hi, good day. So regarding to the issue that you mentioned, typically when you're doing the design for transmission system, we also look at what we call ride-through capability of the units and both whether you're talking about renewable or conventional generation. So we look to ensure that once the system would stay online when you have certain events, and if it exceeds the required timeline in terms of when it should be on, they will automatically disconnect them from the grid itself. So it's not as if you'll have these units online after the fault and still on it while we're basically up doing maintenance or checks on the system itself.
Yes.
I'm not sure if that clears up everything.
Yes, yes, that's true. Yes, that's the IEEE requirement that was mentioned by Christian. Yes.
Right, and the virtual inverters would operate in the same way.
So as I mentioned, you will have to coordinate that because the virtual inertia is way slower, way faster than this disconnection time. I'm speaking about milliseconds response. So, but of course, there will be coordination needed to get the inverters offline in accordance with IEEE. Yes.
Okay, and I'm guessing that coordination is taking place at the design stage.
Yes, yes.
Okay, okay. All right. Any other, I'm seeing another hand raised. Okay, I think this would be our final question. All right, Everton, you should be able to unmute, so you can go ahead and ask the final question.
Well, one of the things I am wondering that Crispin Andrews was talking about is he talking about a village where the main power has gone out and the inverters remain in a state where the islanding effect did not come into effect, that the inverters continue pushing power onto the grid while the grid is out because one inverter not seeing the outage because another one is on, continue to stay on, and that ripple effect goes on. I'm wondering if that is what Mr. Andrews is really speaking to.
I cannot answer that question for Mr. Andrews.
Yeah, but that would be an interesting chat. Oh, he said, yes, that is what he was speaking to. Oh, in terms of the inverters seeing themselves and
yes.
not, okay.
Yeah, so again, it has to do with coordination, and this has to do with the study before, and what is the design requirement of the grid? So should the grid, once it is connected from a main grid, be also in a blackout state, or should it continue on its own? And those kind of this kind of coordination between the inverters will will come from a study that determines how fast this virtual inertia should be, and stop responding in coordination with the requirement that they go offline and to keep the safety of the grid. Yes.
Okay. All right. Thank you so much for that. I hope that note clears up everything for everyone. And definitely, we appreciate that you have been here with us this morning or afternoon, depending on where you're joining from. Thanks to Clint for an interesting presentation. We do appreciate the time and the effort that you've put into it, and it has definitely been a good discussion this afternoon. And we invite you to fill out there's a questionnaire that you should get when you are leaving the room after we have ended this afternoon. So you should get a pop-up for a questionnaire. We ask you to fill it out so that we can get some feedback in terms of how we can serve you better. Thanks to the SICRI team, thanks to the Regional Universities Networking team. Really appreciate your work, and we look forward to you, our participants, joining us again. The next webinar is going to be on the 10th of September. And so you can stay tuned, look out for who is going to be presenting next. And we invite you to join us again and be a part of the conversation. Thank you, everyone, and have a good afternoon.
Thank you.
Thank you.